Hello, everyone. It's nice to see many people again. So today we have Ahina Nandy, who is going to talk about an interpolation between special linear and general algebraic cobordism. Thank you.
Thank you very much, and thank you everyone for coming here to listen this talk. And thanks a lot, Julie, for the shorter and nicer title. So I'm going to talk about an interpolation between special linear and general algebraic cobordism. And part of it, maybe most of it, is based on this archive. So if you find it interesting, I would be very happy if you have a look and tell me if something is wrong or something is nonsense, whatever. So in this talk, what we are going to do is we are trying to translate or extend some result from classical topology to stable motivic homotopy theory. So first, I will start with some topological motivation, or I'll tell you the story of what happened back in 60s and 70s in topology. And then since we are trying to translate all of it into stable A1 homotopy categories, so I will give a very brief construction of that. And then I'll try to say what exactly we are trying to do and sketch a proof of it. And then we're trying to apply it in some computation, and I will try to give some idea of what we are doing nowadays. Okay, it's not good, but let's start with what happened in topology. So we know that in topology, complex-oriented cohomology theories, these have a very central role. So one way of talking about this is, okay, these are the theories which have Thom isomorphism for every complex vector bundle. So you start with some theory, we call it complex oriented. If for every rank in complex vector bundle, you can choose a Thom element in this particular group such that it gives you this Thom isomorphism. And such a choice of such element is called a particular orientation or a particular complex orientation. And we know that complex cobordism, or MU, this is the universal complex oriented cohomology theory. And the fact that this is the universal complex oriented cohomology theory and understanding of this particular theory, it sort of changed the way we look at the classical stable homotopy category. Now, you can say that, well, there are a lot of interesting theories which are complex oriented, but you can say it's a little bit too strong. So you might not want to have Thom isomorphism for every vector bundle, but you might want to have this sort of Thom isomorphism for some specific vector bundles with certain properties. And one of such properties, well, we want to have this isomorphism for vector bundles such that their determinant bundle is trivialized, or their determinant bundle is isomorphic to the trivial line bundle. And in other words, these are special unitary bundles. So among such theories, we have a universal bordism theory, which is MSU, or special unitary bordism. And back in starting from 1950s to say somehow until 80s, the understanding of MU, or complex bordism, it kind of changed stable homotopy theory. But it turned out that all the tools which were used to study MU bordism were not very helpful to study MSU bordism. So at that time, in probably 62, Novikov gave an explanation or some sort of description of MSU-bordism after you invert 2. And Conner-Floyd gave a complete description of torsions in SU-bordism. And these two things together gave us some idea of how exactly MSU-bordism looks. And we are kind of trying to do what Conner-Floyd did for this special unitary bordism for correct notions in the stable A1 homotopy category. So one of their main tool was a filtration of complex bordism MU in terms of the special unitary bordism MSU. And they also very explicitly used the geometric construction of complex and special unitary bordism rings, which we still do not have in algebraic geometry. So we'll not go into that in this talk. So in this talk, we'll talk about if we can extend this part, this filtration of MU in terms of MSU, in an appropriate way in the stable A1 homotopy category. So since we want to extend certain things in this category, let's just look at how does this category look. So first, we need to fix a base scheme, say some S, and it can be done in a more generalized way, but let's just fix for now a Noetherian scheme of finite Krull dimension. And we want to study all smooth schemes of finite type over this, if this base scheme is. And we want to use tools from homotopy theory, but this category of smooth schemes over S, this is neither complete nor co-complete. We can't really do homotopy theory in this. So we do what we usually do. We look at the category of certain presheaves over this category. So this is the P of SMS. So this is the infinity category of space values presheaves over this. And by space, we can also take, say, Kan complexes. It doesn't matter. But we do not study all of them. We need to make sure that the affine line A1 is contractible. In other words, in the more technical words, it would be taking a left Borsfield localization with respect to A1 local objects, whatever that means. And we want to make sure the objects we are studying, those are shapes for Nisnevich topology. So we are not taking all the pre-shapes, only ones which are shapes in Nisnevich topology. Let's not get into the detail of how exactly Nisnevich topology is defined, but this is what is the so-called unstable A1 homotopy category. And now, once we have this, I mean, just like topology, the unstable category is extremely complicated. We don't want our life to be this complicated, so we want to go to the stable one. So again, what exactly we do in topology, we start from the unstable one, take a pointed version of it, which happens to be presentable symmetric monodal infinity category, and we want to invert something. Now the question is, what exactly do we invert? Well, in topology, we invert a smash product with S1. Here, we need to invert smash product with P1, and there are a lot of good reasons why we might want to do that. And one not so good reason, I will just tell now. So here in this presheaf category, we have two circles, very canonical choice. One is just a simplicial usual circle, and the other one is state circle or GM. So it can be thought of as a representable functor that takes X, any scheme, and gives out OX star or the units in OX. Yeah. And it turns out that to get a reasonably good category, we need to invert both of these circles. And that is equivalent to inverting whatever you get after smashing these two circles, which happens to be equivalent to P1. And this is also written as T. So we are inverting P1 or T, and we will use all of them interchangeably. Okay. So now, once we know how exactly this stable A1 homotopy category look, let's go into the analog of complex and special unitary cobordism here. So these are general and special linear algebraic cobordism. So here, I don't know, maybe there are experts, and I need to put some disclaimer. In algebraic geometry, we have very nice theory of cohomology theories of variety, and also like oriented cohomology or any idea of orientation for cohomology. And these are defined using something very similar to Allenbach-Steenrod axioms. And these things, they don't need to be representable in the stable A1 homotopy category. But for the sake of this talk, we are only talking about theories which are representable. So I will not go into possibly non-representable theories. Yeah. So for us, a cohomology theory would be something which is representable in this category, the stable A1 homotopy category. So let's start with some yield, and it gives you some cohomology theory. It is called It's called oriented if we have Thom isomorphism for every vector bundle. And now, since these are theories from the stable A1 homotopy category, these are bigraded, and you need to find out some Thom element in a suitably defined group. the question is, when we say Thom isomorphism, how do we define Thom space in this scenario? Well, this is the, you start with the vector bundle and quotient it out by the complement of the zero section. Now,
I'm sorry.
Yeah.
I might just have missed a thing you said quickly. Why is it bigraded again?
Because we are inverting these two. So for 1, 0, the thing we are inverting, the spheres are bigraded.
Yeah. Okay.
Does it make sense? And we always write, so P, comma Q would be like, you just have to add it up. Okay. Thank you.
Thanks.
So now taking such quotient doesn't make any sense if you are in schemes, but we are taking in the pre-shift category, so everything makes sense. And examples of such theories are motivic cohomology. This is kind of an analog of, say, singular cohomology, algebraic K-theory, and algebraic Cobordism. I will give a construction of algebraic Cobordism. And among such theories, we have a universal one, which is algebraic Cobordism. Just like MU is universal among the complex-oriented ones, MGL is universal among the oriented cohomology theories. And when I say universal, this is universal among the ones which are representable in the stable A1 homotopy category. And in this context, this spatial linear orientation is a little bit more interesting because there are a lot of very interesting theories which are not oriented, but they have spatial linear orientation. That means, well, we do not have Thom isomorphism for all vector bundles, but we have Thom isomorphism for the vector bundles with trivialized determinant bundle. And such examples would be the so-called quadratic refinements of the classical theories. That means Milnor-Witt motivic cohomology, derived Witt theory, Hermitian K theory, whatever these are. The point is, all of these are not oriented, but they have this spatial linear orientation. And among such theories with spatial linear orientation, we have a universal one, sort of universal one. Let's not go into the detail. So this is the spatial linear algebraic Cobordism, or MSL. Panin and Walter constructed this theory sort of to make sure that it has the correct universal property we want. Okay. Since we are going to spend some time with these two bordism theories, algebraic Cobordism and spatial linear algebraic Cobordism, let's look at a very brief construction of these things. So the construction is very similar to topology. People constructed this sort of mimicking topology. So you start with some Grassmannian. This is the Grassmannian of n planes in A n plus m ambient space. And this is the tautological n bundle over it. And you can include it in a like Grassmannian of n plane, but in a bigger ambient space. And you can have the tautological bundle. So now we can consider the infinite nth Grassmannian, or the infinite Grassmannian of n planes. It would be this appropriate sequential colimit. And we're writing it as BGLN, just like topology, but it doesn't really classify rank and vector bundles. It only classifies rank and vector bundles for affine schemes, not for all schemes. But we write it just because we want to mimic topology. Anyways, and when I say we want to see the construction of MGL, I at least want to show how the nth space loop. So this is this appropriate colimit of Thom space of these bundles. Yeah. Okay. And if you know the construction of MU, it's just the same. And it can be given a commutative ring structure. And in fact, it is a symmetric T spectrum. And there is a functor called complex realization functor. So what you do is you start with the category of smooth schemes over some field which has a complex embedding. Now you can take all the complex points with complex analytic topology. So this induces a functor from the stable A1 homotopy category to the classical stable homotopy category. So you start with some motivic spectrum, it gives you back some classical spectrum. So taking such complex points, it gives, if you do it for MGL, it gives you back complex Cobordism MU. So MGL is really our analog of MU. And now, since our another study is MSL or special linear cobordism, we will also see how this was constructed. This construction is due to Panin-Falter. So what we do is you again start with the Grassmannian of n-plane in some bigger ambient space and take the tautological n bundle over it. And now you want to consider the determinant bundle of it and take the complement of its zero section. And the complement of zero section of the determinant bundle of this tautological n bundle, this is our analog of oriented Grassmannian. I mean, similarly, if you just like taking complex points, if you take real points of these things, you actually get back real oriented Grassmannians. Yeah. Okay. And we take this pullback bundle, and similarly as before, we can consider the NH special linear Grassmannian, which is the colimit of the special linear finite Grassmannians. And the NH space of the spectrum MSL is the appropriate sequential colimit of Thom space of this pullback bundle. So this is, so in some sense, this is Thom space of a vector bundle over the special linear Grassmannians. It also has a ring structure. It can be given a symmetric T-spectral structure. We're not going into detail there. And if we take the complex points, we get back MSU. So it really is a canonical analog of MSU. And if we want to extend some relation involving MU and MSU, we better do it with MGL and MSL. Okay. So now, what exactly we are trying to do in this talk? So I gave you the construction to kind of convince you that there exists a canonical map from MSL to MGL. And if you take the complex points, this is exactly the map from MSU to MU, and that is just canonical map which we get from the inclusion of SU in U. And if you remember how we give a canonical orientation to complex Cobordism, here also we have a canonical orientation map for algebraic Cobordism, and it's exactly the same. It's just the first space MGL1, it happens to be, it is homotopic to the base space BGL1 using zero section. It's just like topology. So we have a map. Now we smash these two maps and use the fact that MGL is a ring spectrum. So we get a map. It starts from MSL smashed with this certainty suspension of P infinity to MGL. And if you take a complex realization, we get a map involving MSU, CP infinity, and MU. And Conner-Floyd proved that this map is an isomorphism in the classical stable homotopy category. And because CP infinity has a very natural canonical skeletal filtration, they got a filtration which was useful in their work. And what we want to do is, we want to say that if this map psi, this is an isomorphism in the motivic stable homotopy category or not. And we prove that it is. And if we have that, we can use canonical skeletal filtration of P infinity and get the exact same filtration and then use it for some fun stuff. Okay. Any questions so far? Okay, if not, we'll go to the proof or some idea of the proof. So we want to show that we have this map and we want to show this is an isomorphism in the stable A1 homotopy category. So how do we start? If it has to be an isomorphism in the stable A1 homotopy category, it has to induce isomorphism for some cohomology or some homology theory. Yeah. So first we try to do that computation with some E, some cohomology theory, doesn't matter. And if we want to show that this smash, so you smash it with E, it is an isomorphism. It's just because how homology is defined and the fact that these groups, they They detect weak equivalence in this category. We have to show that the E homology or this map, it induces isomorphism in E homology. Yeah. So why do we do that? Because once we choose something for E homology or cohomology, we have nice computational tools. So we take some oriented cohomology because we have tone spectrum and we know how the base spaces look, and we have a cofiber sequence for them, which gives us a long exact sequence. And we have some description of how this sort of cohomology for finite Grassmannians look, but these are very complicated objects, so we don't talk about them. We go to infinite Grassmannians because those have much better descriptions, and we take the cohomology rings because just like topology, when the oriented cohomology rings of infinite Grassmannians, they have very nice description. So this is something we use, which is if you take the E cohomology of some nth infinite Grassmannian, BGLN, this looks like this. It's a power series ring in the where the variables are Chern classes of the tautological n bundle. It's just like topology. And this is the coefficient ring. And because we have already fixed S, I will next time onwards just write it as E star comma star and nothing more. Okay, so going into the nice place, we have something like this. And it's all about figuring out how this map looks. Because if we can figure out how this map looks, we can figure out how the Easter cohomology of the BSLN or the infinite special linear or special oriented Grassmannian should look. So it turns out that we need some more adjective for the E. It has to be oriented. It has to have additive formal group law. Doesn't really matter for now. And with these adjectives, we know how Easter cohomology of BSLN looks. And since we have started with oriented cohomology theories, we also know how the Easter cohomology of MSL looks. So this is the thing we are trying to compute. And in one side, we know how Easter cohomology of MGL looks. This is already done before. And on the other side, we know how it looks for MSL because we just computed how it looks for BSLN, and then it's just homomorphism. And we know how it looks for P infinity. Now, if you look at this, we want an isomorphism here. So it's just saying that we have to use some sort of Punnett formula here. Yeah. Now, in A1 homotopy theory, it's a little bit more complicated. So what happens is in the classical homotopy theory, the stable homotopy category, it has a single compact generator, which is just the sphere spectrum. In the stable A1 homotopy category, it has infinitely many compact generator, but we can look at the triangulated subcategory, let's just say, generated by the sphere spectrum or the motivic sphere spectrum, which is closed under colimit and extension. And that is a subcategory we call cellular subcategory. So the point is that any standard tool or techniques which work in classical stable homotopy theory is very unlikely to work if you go outside the cellular subcategory. So if you want to have something similar to a Kuhn spectral sequence or actually whatever, we better need to work in the cellular subcategory. But luckily, the things we have here, all of them are cellular. So we can use that. And here we just used Kuhn spectral sequence, in this case, just Kuhn isomorphism, to get that this map, it actually gives isomorphism for Easter cohomology. But we wanted the result for homology. And here also there are some complication with cohomology and homology being dual to each other. That's not always the case, but we need certain cellularity, certain strong dualizability, and some finiteness conditions, which I'm not going into much detail, but it works out. And we get this. We get that, well, after smashing with good enough spectrum E, we have that this is an isomorphism. Okay. So we wanted to show that this map psi was an isomorphism. Now we have that this psi smashed with something else is an isomorphism. Now the next question is, how do we get rid of this extra thing? So we will do a very standard thing which people do in stable homotopy theory. I just want to mention one thing, that for Conner-Floyd, it was enough because they just proved that if you take E to be singular cohomology, this is an isomorphism. And when you have that, if you have, it is an isomorphism after smashing with singular cohomology, and on both sides you have connective spectra. It was not very easy for them to prove, but they did it. You can use Hurwitz isomorphism, and that already gives you that psi has to be an isomorphism. But we do not have anything like that in A1 homotopy theory. So we need to do something else. Now, let's go into some detour. So if you start with some F, which is a map between the unit, the sphere spectrum, we can always talk about, say, completion of any spectrum with respect to F and F inverted spectrum. And usually what happens is, if you choose good enough F, these are easier to compute. And there is a very nice fracture square, it's a pullback square. It connects the actual spectrum E you start with and the E F completed and F inverted with something. So here, what we want to show is, for some chosen F, psi after completing with respect to F and psi after inverting F, that is an isomorphism. And if we can show that, we can use this fracture square, and that should give us the isomorphism we want. Now, well, we can take any element F, but we should take something which we understand well. And our choice of F is the so-called stable Hopf map eta. So this one is just the motivic analog of the classical first stable Hopf map. So how do you write it? So it just comes from the canonical map from A2 minus 0 to P1. But in motivic world, these are spheres. So A2 minus 0 is S3, 2. I'm not explaining why these are spheres or anything, but these are spheres. And so it's a map between spheres. And when we stabilize it, we get a map between the sphere spectrum. So it does make sense to look at any map or any spectrum after inverting eta and completing with respect to eta. And we just want to show that these things are isomorphism. So how do we do that? Let's first do the eta inverted part. So this is our codomain, and here we have this P infinity. It turns out that in the eta inverted category, P infinity is contractible. So this side is already contractible. And also in the eta inverted category, any oriented cohomology becomes contractible. So this is again contractible. And in fact, this map is an isomorphism of contractible spectra. And here, I mean, since in eta inverted category, any oriented cohomology is contractible, this is another reason to study SL oriented cohomologies, because this category happens to be interesting and much more computable. And well, the next best thing you have is SL oriented cohomologies. So that's another reason people are interested in this sort of theories. So we have that, well, at least if we invert with respect to eta, this is an isomorphism, this is done. And now we want to show what happens if we complete with respect to eta, okay? So using the previous computation, we did that when we smash our map with some good enough cohomology theory, it gives us an isomorphism. And one example of such a good enough theory would be motivic cohomology. I'm not going into detail what motivic cohomology is, but it should be thought of as an analog of singular cohomology. Now, this is what we have. And if we start with any commutative ring spectrum, we can talk about completing any spectrum with respect to that commutative ring spectrum. This is just the limit of standard Cobordism construction. So because we have this, we have that this psi completed with respect to this motivic cohomology spectrum. This is an isomorphism. So this is something we have. And we want to use this to conclude that when we complete psi with respect to eta, this also becomes an isomorphism. So now onwards, we will be working over a field. So the base scheme we fix that will be spectrum of a field. Some K, doesn't matter. So we want to compare completion because we have that completion with respect to this motivic cohomology spectrum gives us an isomorphism, and we want to go from here to completion with respect to eta. So how do we do that? And this is pretty general. It's just you can start with any presentably symmetric monoidal stable infinity category which has a compatibility structure. And our example would be this SHK, the stable M1 homotopy category of some field. And the field is important here. And there is something called a homotopy structure. Let's not go into that. Something which has this nice property. It is compatible with respect to the symmetric model structure. And let's start with some connective commutative ring spectrum. So some E of this form. And we have this pi 0, which is just a zero truncation with respect to the T structure. So under certain good enough condition, if you start with some bounded below X, it turns out that completing with respect to E is same as completing with respect to this zero truncation of E. And this was done for stable A1 homotopy category by Lorenzo Mantovani in his thesis, and later is generalized by Mantovani and also Bachmann-Ostwald. So you require some adjective, but this is what we are going to use. So that means here if you put HZ or motivic cohomology, completing something with respect to motivic cohomology is same as completing something with respect to whatever this zero truncation of motivic cohomology is. We'll go into that. And again, there are some adjectives missing, but since I'm not going into the detail, we don't care about it. But you start with some good enough F, and you want to look at how completing anything with respect to pi 0 of 1 upon F looks. And it turns out that for some good enough scenario, and we are working in good enough scenarios, this is same as completing with respect to F itself. And this just means if you take the map F from 1 to 1, like from unit to unit, and consider the cone. So this is just the cone. So what we are trying to say is pi 0 of this motivic cohomology spectrum, if this is same as the pi 0 of the cone of eta, we should be done because, well, that's all we need using this and the previous one. And as long as we are working over a field, this is the case. So with our previous computation, we have that this completion is an isomorphism. And now, because this is same as completing with respect to eta, we get that this sign when we complete with respect to eta, this itself is an isomorphism. Yeah. Okay. Now we have the standard fracture square. It connects this one with respect to the eta completion and eta inversion of this, and it is a pullback square where the second row, the lower row, is completely contractible. So this has to be an isomorphism, and we are done. So right now, what we have is, we wanted to show this was an isomorphism. We have shown that it is an isomorphism, but only if we are working over a field. Yeah, it's SHK. And we want to show it for more general base schemes. So all of it works essentially because we are working with spectra which come from tone spaces of vector bundles over certain sort of Grassmannians. And when you base change, Grassmannians are always compatible. So we can do plenty of base change here, and we can first prove it if you work over spec Z. It works, and once you have it for spec Z, going into more general base scheme is not a problem. So it does work out essentially because Grassmannians are so nice. It's nothing special. Okay. So we have this, and now it's time to have some fun. And so we have that this is an isomorphism, and we can use the standard skeletal filtration of P infinity. And that is this filtration. And these, the things in purple, these are just the cofibers at each stage. So we have a nice filtration, and we can put these bigraded homotopy groups like this on, I mean, on the quotients of this filtration, or cofibers, whatever I want to say. And that should give us a spectral sequence. And we do have something of this sort. And as you can see here, convergence, it's not a problem. And we have figured out how these maps in the E1 page looks, because these maps, all the blue ones, these essentially come from maps of this sort. Yeah, from one cofiber to the previous one. And I mean, you have to put some homotopy group here, and then from here to the previous one. So it is very similar to what happens if you start with, say, real projective space. And if you take something like RPN by RPN minus 1 and take this map back to RPN minus 1 by RPN minus 2, and I mean, the homotopy groups of them, it turns out that in case of real projective spaces, these maps are depending on at which end you start. These are either 2 or 0. And in motivic homotopy theory, in most of the cases, we'll see that sort of that analog of 2 should be eta. So it's very similar to what happens in the case of real projective spaces. We have alternatively eta and 0. And here, these things, they converge to the appropriate homotopy groups of MGL, which we are assuming in certain scenarios we know, and we want to use that information to get information about how these things for MSL looks. So we have got something, and this was done before for at least characteristic 0 fields. It turns out that maybe it doesn't make much sense to go into the detail. So we can talk about, say, pi p of any spectrum, which is just this thing. So the p is the fixed, c is the difference between the two gradings. And if you fix p to be 0, which is the easiest case to compute, it turns out that the pi 0 of MSL, whatever it is, if you divide it by eta, you get whatever it is for pi 0 of MGL. And that happens to be Milnor-K theory of the field you start with. And at least for characteristic 0, we know this is the so-called Milnor-K theory, and all of it makes sense, because when you start with Milnor-K theory, you get quotient by eta, and that does give you Milnor-K theory. So it seems like it is true. It should make sense. And there is something else I want to talk about. I was planning to write down here, but okay. So in A1 homotopy theory, I mean, one of the reasons people started looking at this table A1 homotopy category was they wanted to have a spectral sequence connecting whatever we want to call motivic cohomology to algebraic K theory, whenever algebraic K theory is representable in this category, which is not always the case, but at least as long as we are over field, everything is fine. And so they wanted to have some analog of Atiyah-Hesburg spectral sequence, and there is an analog. So there is a filtration called slice filtration, and that filtration gives a spectral sequence called slice spectral sequence. And when we want to have this slice spectral sequence for algebraic K theory or KGL, it gives us something where at the E1 page you have this motivic cohomology, and it converges to whatever this stable homotopy groups of algebraic K theory. So it's exactly like Atiyah-Hesburg spectral sequence. And when you want to start with this slice spectral sequence of any spectrum, the information you need is how the slices of the spectrum look, because in the filtration, the slices are exactly the quotients. And then you want to start with, say, well, you know the slices, and you at least can figure out how the E1 page look, and in most of the cases, how the E2 page goes. and then you have to do something. So it does make sense that we want to compute the slices of MSL. And yes, yeah. And these slices, this S0 and S1, I have written it down, but you can have actually SQ and Q can be any integer. These are actually triangulated functors. So if we have a filtration of this form, so these are the small ones, these are triangles, so because these are cofiber sequences, and when you put this slice functor over them, they preserve the triangles. So these sort of filtrations are quite useful if you are trying to compute slices, and we do some of them. And yeah, this computation was done before, and as long as we take characteristic zero field, we can also compute another one slice. And we are trying to compute some more slices nowadays. Yeah, okay. That's all I wanted to talk about. Thank you.
Thank you very much. I'm gonna stop there.